Welcome back. In this video, we'll be talking about diagonalizable matrices a bit more. We'll see this corollary. In the last video, we actually proved that the geometric multiplicity of an eigenvalue is always less or equal to its algebraic multiplicity. And we also had from before that if the sum of the geometric multiplicities is n, then A is diagonalizable. So I want to put these two together. All right, so I want to understand how a matrix can fail to be diagonalizable. So let A be a square matrix. A is not diagonalizable if and only if at least one of the following things are true. So there are two separate issues that you could encounter. First, the geometric multiplicity of one of its eigenvalues is less than its algebraic multiplicity. And so you don't get enough eigenvectors. Second, the characteristic polynomial of A does not factor as a product of linear polynomials. And so this one would mean that you don't get enough eigenvalues, period. Okay, so that's two different things. Those are the two different things that could happen. Let's see why. So we know that the summation of the geometric multiplicity of the eigenvalues is less or equal, that's from the last theorem, sum of the algebraic multiplicity. And that's like counting the number of factors, linear factors that the characteristic polynomial has. So the most it can have is the degree, which is n. And so A is not diagonalizable if and only if that sum is less than this one. So either this one or that one are not equal. So either the sum of the geometric multiplicity is less than the sum of the algebraic one, or the sum of the algebraic ones is less than n. So that means, let's translate those, either for one eigenvalue lambda, the geometric multiplicity of lambda is less than the algebraic multiplicity, right? So each one is less or equal. So if it's actually strictly less, that means one of these has to be strictly less than one of those. Or when you look at the number of factors, so these count the number of linear factors, and that PA of x has, it doesn't have n. So they're like an irreducible quadratic somewhere, something like that. PA doesn't factor in linear terms. So it doesn't have n root counting multiplicities. It does not factor in linear polynomials. Right. Let me say the second one is a bit lame. And it's a bit lame because we could get rid of that one if we worked in the complex number instead of in the real number. If we allow complex eigenvalues, then any polynomial would factor with n different roots counting multiplicity. And so the only way a matrix could fail to be diagonalizable over the complex number is if there's an eigenvalue that has geometric multiplicity less than the algebraic one. And that we cannot get rid of. All right. So let's look at the following one. This is a bit complicated, but I really like it, so let's go through it. The following proposition gives necessary and sufficient conditions for two diagonalizable matrices, A and B, to be similar. So we've been talking about when the matrices are similar and we wanted to get conditions. What we'll be able to prove is we'll be able to prove something very, very specific for diagonalizable matrices. For other matrices, we actually would need to work harder. There's something called Jordan blocks that determines what matrices that are not diagonalizable could look like. And once you see that, you can get something precise for all matrices here. All right, so Let A, B be two diagonalizable matrices, then A and B are similar if and only if, and this is quite good, they have the same characteristic polynomial. Now, this is not true for matrices in general, but if they're diagonalizable, then that's enough. In fact, I can actually give you the P if I have a basis of eigenvectors for A and I have a basis of eigenvectors for B. And let's say that we've put them in the same order in the sense that the matching eigenvectors have the same eigenvalue. So V1 and W1 have eigenvalue lambda 1, Vn and Wn have eigenvalue lambda n. Then B is P inverse AP, and P is going to be the matrix that you get from putting the vectors V and the vectors W in a matrix, and you just need to invert the W matrix. All right, so let's prove that. For the first part, one direction is already done. This direction is already done. So let's assume that they have the same characteristic polynomial. And so those characteristic polynomial factor in the same way. And so that means A and B have the same eigenvalues, but more than that, the algebraic multiplicity is the same as well, since the polynomial is the same. But then that means, since algebraic multiplicity is the same as geometric one, when they're diagonalizable, that means that A and B have the same eigenvalues with the same geometric multiplicity. And so if we look at what A's E corresponds to, A corresponds to a diagonal matrix with those eigenvalues on the diagonal. But these are the same one as for B with the same frequency, and so this would be the same as B. And since we've proven that if A is the same as D and D is the same as B, A is the same as B, A and B are similar. Okay, so really, if they have the same characteristic polynomial and they're both diagonalizable, they're similar to the same diagonal matrix, this one, and so they're similar to each other. Right, that's nice, but we actually would like a recipe for P, and so let's check that this recipe works. All right, so I'm going to give a name to these matrices here. So let's say QA, because it links back to the matrix A. And let's call the other one QB. One thing to notice is if I multiply QA by EJ, well, I'm going to get the jth column, so I'm going to get VJ, and QB of EJ, that's going to be WJ. All right, so that means if I apply P to WJ, so we said P was QB inverse QA of WJ. Well, here if I sent QB to the other side, I would get that EJ is QB inverse WJ. So this is EJ. And QA EJ, that's going to be VJ. Right, so if I apply this matrix to an eigenvector for B, I get an eigenvector for for A, sorry. And notice that this is what we wanted. This is what we had. Where was it? Man, we've worked hard. Yes, right here. That's been a while. So V is an eigenvector for A if and only if P inverse of V is an eigenvector for V. Okay. So that P matches the eigenvectors just like we wanted. All right, here we are. All right, so let's check that P inverse AP is B. All right, so let's write what that means. P is QA QB inverse A QA QB inverse B. I mean, we could do it like that, but I think it's a tiny bit more convincing if I actually send the QB to the other side. So what I'm going to check is that QA inverse AQA equals QB inverse BQB. All right, so let's check that. What happens when I apply this to, sorry, I forgot the QA. What happens when I apply this to EJ? I'm going to get QA inverse A. QA EJ we said was VJ. And then I'm going to get VJ is an eigenvector, so I'll get lambda J VJ. The lambda J is going to come in front since it's a constant. And then when I'm going to apply QA inverse to VJ, I'm going to get EJ back. Same thing for QB, sorry, B. So let's just say similarly, it's the same argument, equals lambda J EJ. All right, so that means that jth column of one is the same as the other one. In fact, we could actually give that matrix and so if I isolate B in that equation, I'll get QB, QA inverse, A, QA, QB inverse, and that's my P and my P inverse. All right, so it's really the same idea as this proof. It's just that I actually give you a matrix here that's going to be your QA. I give you a matrix here that's going to be your QB, and then we kind of compose them to get our P. All right, in the next video, we'll actually apply this recipe to find the matrix P.